Also, if, do you want me to upload these to the Dropbox or something?
We could do that. I also have one file from yesterday's lecture. I have
Okay.
to upload it at some point. We can do that at some point. Okay.
All right.
Good. Okay. So let me share screen. Okay. So
Sir,
yes.
so when you say quantum fluctuation, what do you exactly mean by fluctuation?
I don't know what is the meaning of the question.
You said when we drop the temperatures.
Yeah. So the quantum system always has quantum fluctuation, right? There is a certain amount of quantum uncertainty in determination of any physical observable, right? So, but the thing is that like those quantities are much smaller compared to the thermal uncertainties that the system would have. Let's consider, say, a simple example. Suppose you are considering, say, a metal, okay, at room temperature, say, okay. Then the energy available at room temperature for that material is K times T, okay, and T is about 300 degree Kelvin. So roughly about 11,000 degree Kelvin is about 1 electron volt. Okay, so at 300 degree Kelvin, you have some few tens of milli electron volt energy is available. Okay, so that entire energy could be soaked up in, say, lattice vibrations in or in the kind of motion of charged particles in the system. Okay, so if you are trying to study, say, quantum fluctuations of, say, particle sitting, atom sitting at the lattice versus the thermal fluctuation of the lattice, the thermal fluctuations will dominate much more. Okay, simply because this much amount of energy is available which can be exchanged with the environment. Okay, as against quantum fluctuation which is intrinsic to the system, which is of order h bar. So those numbers are very small unless you really go to very low temperatures where you can suppress thermal energy effects. Then only the quantum fluctuations would be important. But quantum fluctuations are always there in the system. It is just that if the thermal effects are much larger, you can just completely ignore doing computation of quantum fluctuations. Okay. So quantum fluctuations are always there in the system.
Okay.
Okay. Compare that with, so this is a realistic system. Compare that with, say, a model. So suppose you are studying a classical spin system. Okay, then of course there are no quantum fluctuation because it's a model in which you are studying precisely the classical behavior of the system. Okay, there are no quantum fluctuation no matter at what temperatures you. Okay, so as against studying the intrinsically quantum system, so all realistic systems are essentially quantum. Only thing is that in a regime in which quantum physics is not important, you will study only classical physics. Okay.
Okay.
Okay. So I just wanted to step back a little. So we looked at monoatomic ideal gas last time, where we wrote down the energy E to be some more P square over 2m, and then we wrote down the entropy of the ideal gas in this particular fashion. And from that, we determined temperature, pressure, and also the specific heat of the system. We showed that the ideal gas satisfies the gas law, ideal gas law, and we also showed that the adiabaticity parameter can be shown to be 5/3 in this particular case. Okay, so this is what we did and stopped last time. So today we'll look at canonical ensemble. So canonical ensemble is used to describe a system which is in peak contact with a heat path. Okay, so contrast that with microcanonical ensemble, where no energy is exchanged with the environment. System is totally isolated. In this case, the system is coupled to heat bath. Therefore, there is some exchange of energy with the heat bath. Okay, but you still do not exchange, say, particles with the heat bath. Okay, so in that sense, it is still a restricted kind of situation, but more relaxed compared to, say, microcanonical ensemble. Okay, the probability distribution for the system can be obtained by treating this entire system as an isolated system. That means take the system plus the heat bath, and that entire stuff you can treat as an isolated system. Use microcanonical ensemble to describe this isolated system, and then infer information about the system that you want to look at and write down the corresponding canonical partition function, for example. Okay, so that is the kind of approach we will take. Okay, so of course, when we do this kind of when we take this kind of approach, we also need to assume another thing, that the heat path is much larger than the system. Okay, so in that sense, if there is an energy exchange between, say, heat bath and the system, the change in the energy, or change of the in the temperature of the heat bath is negligibly small. Okay, so if the heat bath is that large, then one could kind of effectively say that the energy spectrum of the heat bath itself is essentially continuous, as against the energy spectrum of the system, which could be thought of as a discrete spectrum of the system compared to the heat bath. Okay, so of course the system itself may be reasonably large and may actually have quasi-continuous spectrum, but compared to the heat bath, that spectrum is still discrete. In the sense, if you pick a particular energy for the system, in the neighborhood of that energy, heat path may have a large number of energy levels. Okay. Okay, good. So let Pi be the probability of finding a system in a particular microstate I with energy Ei. Then Pi for the system is actually a measure of what is the fraction of the energy levels of heat bath which are compatible with the energy Ei. So that's what I meant by saying that, like, heat bath may have large number of energy levels which are essentially treated continuous, and for a fixed energy of the system, heat bath may have a kind of a band of energies available, and Pi is actually just a measure of that fraction of energies of the heat bath to which the microstate I can talk to. Okay, fine. So one could try to take a ratio of probabilities of these microstates, say microstate J and microstate I, and that can be written in the following way. So the number 1 that I have written corresponds to having exactly one state. Just give me a moment, I have got some messages. Just give me a moment. Somebody wants a Zoom link for this course, so I'll just send that. And Okay. Sorry, I just had to kind of send a message to a couple of students who wanted to attend this lecture itself. Okay, so this Pj by Pi, that ratio of probability that we are trying to compute, the factor 1 that we have written is the number of states of the system that are available. And as I said, that the spectrum of the system is considered discrete compared to that of the heat bath. And so that is the reason why one is writing down 1 for per microstate. And omega b is actually the density of states for the bath. And so this Pj by Pi is basically a ratio of states available for microstate J versus microstate I, where delta E is the energy difference between the energy of the microstate J versus energy of microstate I. So of course, you know that the that omega b is related to entropy by a logarithmic relation. So this quantity can be written as exponential of the entropy corresponding to the states that are of the heat bath that are available, and we can write down that expression in this particular fashion. Okay. So what we could do now is that if the energy difference between these two microstates is small, that means if delta E is small, then what we could do is we could expand this quantity. Okay, so that means differentiate the entropy with respect to EB, and of course, or if you want, you can Taylor expand this quantity. The leading term of SB would cancel with this term, and the term proportional to delta E will survive, which would be a derivative of the entropy with respect to in EB times delta E. Okay, so that is what we have written out here. This is delta E, and derivative of S with respect to EB is just 1 over T. Okay, that is the thermodynamic relation that we had derived yesterday. So this quantity essentially becomes minus EJ minus EI upon KBT. Okay, so that basically tells us that these probabilities are essentially proportional to exponential of minus beta EI. Pi is proportional to that. Can't figure out the number here simply because that could just cancel in this ratio. Okay, but at least it gives us a picture as to where it is going. Okay, so fine. So we can write down the canonical partition function by using this fact, and we can write down canonical partition function as summation over I exponential of minus beta EI. Okay, of course, Pi are basically then this exponential factor divided by Q. Okay, so from this expression one can determine what was the proportionality factor, which in this ratio would have just cancelled out between them. Okay, is there a question? Hello? Okay. Okay, so so once we have figured out what is this probability of finding a microstate I and corresponding canonical partition function, we can determine the free energy of the system by just taking log of this partition function and multiplying by 1 over beta. Okay, so
sir,
yes.
Sir, so in thermodynamics, we define F as E minus Ts. So that means that if you want to make a system which is with a reservoir coupled with a reservoir of temperature T, we don't need to put E energy. We need to put F energy into it, and the extra Ts energy is supplied by the reservoir. So
Yeah.
how does that link to this formula that we have, the statistical mechanics formula?
Yeah, so we'll derive it in a moment. Basically, this is what I was going to say, that you will write down Qn as E minus Ts.
Okay.
Okay.
Sir?
Yes.
So this I, does it label a particular energy state or energy level? Because if there is degeneracy, we
Yeah.
can simply put this omega ei, and this omega ei is e to the power minus.
That is right. So we are
yeah.
assuming so omega b is the degeneracy corresponding to the heat bath. I'm assuming that the omega ei corresponding to the system is just 1. That is why I had written the factor 1 basically in this expression. Okay. So I'm assuming that there is no degeneracy in the system.
Okay.
Okay. Okay. So one can write down the free energy as a log of the canonical partition function and derive quantities like internal energy, which is the average value of the energy, which can be computed in this particular fashion, which is just taking the derivative of f with respect to t or beta rather. Okay. So there's a way of writing that in purely in terms of free energy instead of worrying about writing it in terms of the Qn. Okay, so one could do this computation once you know what is the free energy. For a microscopic system, the canonical partition function is typically written in terms of density of states. Okay, so remember that like even if the system is small, okay, one would still like to know what is the energy what is the distribution of the spectrum and what is the density of states corresponding to a particular energy. Okay, so that quantity is basically related to the entropy of the system, exactly the way we had written it for the heat bath. So okay, so we write down GE as just the exponential of the entropy corresponding to the to a given energy, and delta is basically a small energy band about which one is trying to determine the density of states. Okay. Okay. So in that, if one kind of defines it in this particular fashion, then one could write down the canonical partition function in terms of a sum over energy, or if you kind of allow one to replace sum by an integral, then it will be basically dE upon the energy band delta times exponential of minus beta E minus Ts. Okay, so that is how you actually get this thermodynamic relation to be F being related to E minus Ts. Okay. Now remember that the average energy is something that we had computed right here, which is same as the internal energy. You could write down this expression again in terms of internal energy as U minus Ts for some average value of E. Okay, so that is the kind of computation that one could do in the canonical ensemble. So let's revisit the ideal gas problem. So if the ideal gas is at temperature T and contains N particles, and it is put in a container of volume V, then we can write down the canonical partition function for this factor of for identical particles 1 over n factorial times the phase space integral of e to the minus beta E. Okay, and this integral is kind of straightforward to do simply because this factor p squared gives a Gaussian integral for p. And we can just carry out that Gaussian integral by using the following formula. Integral dp exponential of minus beta p squared upon 2m is just square root of 2 pi m kbt. Okay, or 2 pi square root of 2 pi m by beta. It's the same stuff. Okay, so this is just a kind of canonical Gaussian integral, and so one can just use this for each one of these integrals. They are all decoupled, so there is no complication in doing that. Take this and just take the 3nth power of that. Okay, so 3nth power is written a little differently here. We write down this factor to the 3 by 2 power, and the whole thing is taken to nth power. V to the n, of course, comes from the space integration, and 1 over n factorial is the one sitting out here. So that's how you get the canonical partition function for the system. And we could compute the free energy for the system, and that is using the formula minus 1 over beta times log cube would give you expression which is like this. Okay. So it may look like it's an odd -1 sitting around here, but this factor comes from this Stirling approximation of n factorial, which is n log n minus n, and that is that minus n factor sitting around there. Okay, so so that is the free energy, and of course we could have written this quantity kind of in the same fashion, because this is the way it would appear in the entropy formula. Remember, we had written it last time. We also went through that today. Maybe I will just go back a little, and so this it's like that. Okay, so yeah, so we could kind of but I choose to kind of write it in the reverse fashion simply because this is a factor which is proportional to what is called the thermal length of the system. So if you are studying a system at temperature T, then there is a characteristic length scale which is available with respect to which all fluctuations could be measured, and that is what is called the thermal wavelength. Okay. Now, when one is talking about comparing this with, say, quantum fluctuations, then one is basically trying to ask a question: when is the de Broglie wavelength is comparable to this wavelength? And whenever that happens, then you would say that the quantum effects are important, and in that case, you would want to not ignore quantum corrections to whatever computations that you would do by just studying the thermal partition function. Okay. Now remember that de Broglie wavelength is proportional to h by p, and p is of course the momentum, average momentum of the particles in the system. And if the system is cooled down to very low temperature, then the momentum is very, very small. And if the momentum is small, then the de Broglie wavelength can become large and can actually become comparable at low temperatures to this quantity, and that is the place where one would be interested in studying the system. Okay. Okay. So given that we know F, we could again compute other thermodynamic quantities like U using this formula, which gives you 3 by 2 nkt, which is a good thing because this is related to equipartition theorem. We can compute entropy, and this is a formula that we had written down last time. I think I noticed some factor of 3 written in the denominator, which is probably a typo. I'll have to correct that. But barring that, this formula is same as the one which we had written down last time, which was completely based on simple phase space volume kind of considerations. One could also compute chemical potential by differentiating the free energy with respect to n, and we get this formula, okay, which is kind of trivial to compute in this particular case. Okay, so let's move over to the grand canonical ensemble case, and the grand canonical ensemble describes the system. But before that, any questions about this?
Sir, just to clarify,
Yeah.
We are taking the definite 1 by T equal del S by del E or minus del S by del E as a definition, right? For
Yes.
temperature.
Yes, yes, yeah.
And similarly for chemical potential and pressure.
That is right, yeah. Yeah, so
okay.
We are not deriving it from any first principles out here. We are taking them as definitions. Okay. Any other question?
But so that is borrowed from first law of thermodynamics, isn't it? Second law. Yeah.
No, well, it depends. The entropy related quantities are related to second law, yeah. So
yeah,
what is
so TDS is DE
That is it.
minus, yeah,
Yeah. So,
PDV.
but we are not deriving it right now. Okay. So
Yeah.
yeah. So in that sense, they are taken as definitions.
So when we make connection between thermodynamics and statistical mechanics,
Yeah.
the only thing we take is S equal to K ln omega. That, except that everything comes from that.
That is right. So but for that I will have to write down a microscopic model from which I derive S, and then everything else could be derived. But for that I need to use these formulae, right? How do I define, say, chemical potential of the system, or say pressure of the system, right?
There we are using thermodynamics formula, and from
exactly.
by putting S we are getting.
That is right. Exactly. So you derive S from microscopic model, but starting from S, relating it to, say, temperature or to pressure or some such thing, you use these thermodynamic relations.
Okay.
Any other question? Okay. So if there are no questions, maybe we can kind of start looking at the grand canonical ensemble. So the grand canonical ensemble describes a system which can exchange both energy and particles with the surrounding, and in that case, what one can do is to introduce a conjugate variable for every variable that describes the system. Okay, and these conjugate variables are typically referred to as chemical potentials. It's kind of a misuse of the word, but of the phrase, but nevertheless it is the easiest way to kind of describe a system. So what one does is that that we introduce chemical potential for every conserved quantity in the microcanonical ensemble. Okay, so imagine you have a system in which there are multiple conserved quantities. In the microcanonical ensemble, everything is conserved exactly. So in that case, there is nothing that you really need to worry about. Okay, but as you go from microcanonical ensemble to canonical ensemble to grand canonical ensemble, you would allow many of these quantities to be exchanged with the surrounding. Okay, and typically the approach to understanding the ensembles corresponding to systems is to treat the bigger system as an isolated system. So you may have certain quantum numbers, like say a charge quantum number or some spin quantum number or some internal quantum numbers like isospin or some such things. They may be conserved. Okay, but if the particle exchange happens, or if some charge exchange happens between some class of particles of the system with some other class of particles in the environment, the total system being treated as an isolated system, the charge would still be conserved. Okay, but the system may lose or gain some charges when it exchanges particles or some quantum numbers with the heat bath. Okay, so what one does is that, like, that you may have a system which may have n conserved quantities. You turn on n such fugacities. Okay, and the corresponding quantity written in the exponent is typically still called chemical potential. Okay, so in our case, the situation is simple. We have only simple conserved quantities, energy, which we kind of quote unquote gave up by the time we went to canonical ensemble, and the other conserved quantities was particle number, which we would kind of give up when we'll start talking about grand canonical ensemble. So for grand canonical ensemble, we'll turn on a chemical potential mu for particle number. The corresponding chemical potential for energy is, of course, beta. Okay, so similar conjugate variable in this case is mu. Okay, so the equilibrium state therefore would be described in terms of these two chemical potentials, namely temperature, which is the one which is conjugate to energy, and and mu, which is conjugate to the particle number. Okay, so the probability now that n particle system that one is looking at is in a particular microstate I, which has energy EI, can then be written in the same fashion that we had written down earlier for the canonical ensemble, but now with two fugacities or two chemical potentials. One is of course the original beta factor and a factor mu. Okay, so using this, so I have kind of been a little cavalier in writing this. I should have written down some normalization factor, or I should have written down some proportionality factor here. It's not really exactly equality, but okay, I'll correct it, I think. Okay, so but with this kind of weight function for finding a particle, for finding an n-particle system in a particular microstate I, one can write down a grand canonical partition function Xi as sum over all particle numbers plus a sum over all microstates I e to the minus beta ei minus mu n. Okay, so so in this particular case, of course, we can clearly see that the energy, besides energy exchange, the particle number is also not being conserved, and is therefore the total partition function is summing over all possible particle numbers. Okay. Once you write down this partition function, one can use this to write down the corresponding free energy, which is called G, which is minus KB times log of Xi. Okay. Okay, so if you want to know what is the grand canonical partition function in terms of microstates, then then it's the same formula basically, but we are going to write it in the form in which basically we are going to convert this sum over particle number to an integral over particle number. It's kind of an approximation, because particle number is really an integer, but in the large and limit it really doesn't matter. Okay, and so you convert these into integrals and you write it in this particular form. Okay, now the advantage of writing it in this integral representation is that you can ask what is the most probable value of the energy of the system as well as the number of particles, given that both these quantities are not really conserved in this particular ensemble. And all you need to do is to basically do a saddle point approximation and find the extremal values. Okay, and so in the large n limit, excuse me. In the large n limit, this extrema are given by say E is equal to E bar and N is equal to N bar. And at around this extrema, you can now compute the thermodynamic quantities by holding E is equal to E bar or N is equal to N bar to compute the other quantity. For example, if you want to compute chemical potential, then you can differentiate entropy with respect to N, holding the energy to be the average energy E bar, and so on. Okay. Similarly, 1 by T is determined by holding the number of particles fixed. Okay, so like in the canonical ensemble, here the free energy, which can be written as U minus Ts minus mu n, but the internal energy itself is can be written as TdS minus PdV plus mu dn. So if you want to look at the differential of the free energy, then you can kind of use this relation to soak up some of the pieces. Like, so when you look at dg, you have terms which are like TdS and mu dn coming from here, and you also have terms which are like SDT and nd mu kind of terms. Those are the terms which would end up surviving. So what we would do is we just cancel the du with other differentials and write down dg in terms of SDT, nd mu, and PdV. Okay. Fine. So yes.
Sir, is there a difference between U and D?
Sorry.
The E that you defined in this integral,
Yeah.
the E bar. Is E bar and U same?
E bar and U are same. Yeah.
Okay.
Yeah. E bar and U are same. In fact, that is what we had done even in the canonical ensemble. Remember?
Yeah.
E bar and U is basically the same quantity. I'll just go one step above. Here.
Okay.
Okay. By the way, I have updated the file in the Dropbox. So I should have said this in the beginning that where am I? Okay, I'll find my this thing. So I should have said it right in the beginning that I have updated the file. So in case for some weird reason the audio is okay, but the screen is not clearly visible, you can always kind of look at that file. Okay. And the amount of stuff that is there in that file is the same amount of stuff which is there in this file also. So in fact, I'm projecting the same file really. Okay. So in case there is a connectivity problem or something. Okay. Fine. So what we could do is that we can turn on, we can write down grand canonical partition function by defining the fugacity, which is called Z typically, which is e to the beta mu. Remember, we had written down this quantity earlier. We have this e to the beta mu times n kind of factor when you write down the grand canonical partition function. So this expression would, this expression would look like z to the n kind of factor if you define z to be e to the beta mu. Okay. Now, if you remove that piece, the last part, okay, e to the beta mu part, then what you are left with is e to the minus beta ei, and that is pretty much like the canonical partition function of the system, right? So therefore, if you hold number of particles fixed inside the grand canonical partition function, so look at this expression for Xi, and in the Xi expression, if you pull out this factor and write z to the n for a fixed n, then that expression multiplying that is just canonical partition function. Okay, so therefore it's going to look like this, that there's a sum over n, and for every fixed n, you have z to the n times qn, where qn is the canonical partition function. Okay. Fine. So of course we are going to sum over all possible values of n here, and so this is kind of an infinite sum. But let's look at some special cases where something more interesting can be done, and that is the ideal gas situation. Ideal gas is non-interacting system, and remember all those integrals that we had to do for computing Qn were just Gaussian integrals for every momentum variable. And as I said, that those Gaussian integrals were kind of completely decoupled, and in that sense, those integrals were just nth power of a simple integral. Okay, so therefore we can write down Qn for an ideal gas as just Q1 to the n. Okay, because of the fact that this thing just decoupled. Okay, and except for the fact that because the particles are identical, Qn is not just Q1 to the n, but there is a combinatorial factor that you need to kind of take care of for the particles being identical. Okay, so Qn is really Q1 to the n upon n factorial, and this by now should be familiar. This is just the result of that Gaussian integral, and this is just the spatial integral to get the volume. Okay, so this Qn that we are going to write down, if we choose ideal gas, then that expression is going to be very simple. So Xi in this case is going to look like an expression of this type. It is Z times q1 whole to the n upon n factorial. Okay. But that is a very simple expression because this is just a power series, Taylor series expansion of an exponential function. So you write down C as exponential of zq1. Okay. Of course, we cannot be this lucky all the time. This happens simply because we are looking at ideal gas where particles are not talking to each other. They are free. There is no interaction even with the potential. Okay. So can't get things simpler than this. So, but in this simple situation, you can write down grand canonical partition function in a nice closed form. Okay, so once you get that, then we see something very good happening, because if your Xi is written as exponential of something, your free energy is a very nice function, because free energy is related to the log of the partition function, and that log will just kill exponential, and therefore G is related to is proportional to Z times Q1. Okay, so that is one great simplification that happens in the grand canonical partition function. Okay, good. So once you know G, then it's kind of easy to compute various quantities. For example, average number of particles. This is something that we wanted to compute. This thing we said that we can compute thermodynamic quantities by figuring out what is the extremum for which the E has some average value and N has some average value, and then kind of proceed with this. But now, after having determined the partition function for a particular system, simple but still system, if you can get the excuse me, if you can get the free energy in a simpler form, closed form, then you can compute the average value of number of particles or energy and so on. Okay, so in this particular case, n bar is just minus dg by d mu, and but mu, remember, is sitting in the exponent here. Okay, so therefore, if you look at that quantity is still proportional to this z times q. Okay, now remember, g actually has a 1 over beta sitting around here, so therefore dg by d mu, which brings down a beta, actually just cancels with this kbt factor. Okay, and therefore n bar is just z1 times q. Okay, so you can check this, that this n bar equation also produces this expression for the chemical potential. Okay, anyway, yeah.
Sometimes this comes as a shock to me when, in this slide, when we write this as an exponential, we are actually not taking any upper bound on the number of particles.
That is right, yeah.
And then we calculate the average number of particles to be
yes.
ZQ1.
That is right, yes.
So this I can't understand actually.
Well, in the grand canonical partition function, there is no number conservation, right?
Yeah.
Right. So the system could have the number of particles ranging from any value for n, which could be small, going all the way to the large values, right?
Yes.
So you are basically just, this is of course a mathematical sum. Okay. You could of course ask a question that, like, well, the assumption was that the heat bath was much bigger than the system, but yes, true, but this is a mathematical expression which allows you to kind of write down the grand canonical partition function in a closed form. Okay, given that there is no limit on how many particles could be entering or exiting the system, you cannot rule out that n could take arbitrarily large value, right?
Yeah.
Okay. Now, of course, in realistic terms, you could of course say that, like, even in the universe, the total number of particles is finite. Okay. So in that sense, this is always a mathematical idealization of doing a particular computation. Okay. So, so don't get shocked if it is done this way next time around. Yeah, so all you need to actually check really about these kind of expressions is that as the average value of n becomes large, the corresponding partition function is actually bounded. If it is not, then you are in trouble. Okay.
Yes.
Okay, so going back to the G again, sorry, I keep flip-flopping. If you hold, say, if you hold the T and mu constant, okay, then your G is really proportional to P times V, okay. It should have been capital P, okay. So that is what we are going to do, that if you hold the temperature and chemical potential fixed, then your Gibbs free energy basically just minus P times V. Okay, but remember that G itself was known to us. Okay, G is basically minus KBT times Z times Q1. Okay, but Z times Q1 is also something we know, because Z times Q1 is the average number of particles. Okay, so this expression tells us that G is equal to minus N times KB times T. Okay, so if you substitute that up here, then we actually produce the ideal gas law, because PV is equal to N bar times KBT. Sorry, this should have been small k. Okay, fine. So, so if for a fixed chemical potential and temperature, we actually managed to produce the ideal gas law by just looking at the at these expressions and using the average value of number of particles of the system. Okay, good. So now that the average value of the number of particles is Z times Q1, we can use this relation and try to substitute it back into the partition function and try to see how that partition function is going to look like. Okay, so what we find basically is that you can ask questions about, like, what is the probability of finding the system like with n particles, and what is the probability distribution for that in the ideal gas approximation. Okay, so if you want to do that, what you need to do is basically write down a probability which involves n particle system. Okay, so something like Z to the n Qn. If you are doing ideal gas, then it is just Z times Q1 to the n factor. Okay, but you are looking at a probability of that in a full system. So therefore, you should divide by Xi. Okay, so if you do that, then our expression is going to look like the probability of finding n particles in the system would look like Pn, which is Z Q1 whole to the n, divided by, of course, n factorial, because that was identical particle piece that you need to filter out, times Xi, which is exponential of Z Q1. Okay, so that is, of course, without that, the expression would have been different. This is normalized probability, right? But we know that n bar is Z times Q1. Okay, so whatever Z times Q1 appears up here, we could just replace that by the average value of the number of particles. Okay, so if you do that, then our probability takes the form n bar to the n, which is this expression, okay, divided by n factorial, which is due to identical particles, and then e to the Z Q1 itself again can be written in terms of n bar, so it is e to the minus n bar. Okay, and this is what I meant by saying that this distribution actually follows a Poisson distribution. Now, it is not apparent here, but once you reach this point, then you can see that this is exactly the Poisson distribution. Okay, so the probability of finding the n particle system within the ideal gas approximation actually has a Poisson distribution. Okay.
Sorry, I don't really get why. How did we write this? That probability of finding n particles in a system would be this.
Oh, because see, if you want to find n particle in the ideal gas setup, then n particle set expression is just z to the n qn, right?
Yes.
Right, but that quantity is just z to the n q1 to the n upon n factorial, right?
Yeah.
Okay, so that is the kind of amplitude, quote unquote, of
Oh, okay. Okay.
n particle thing. But in a full system, finding an n particle system is this divided by the full system, right?
Mm-hmm.
So therefore, I write down z q1 whole to the n by n factorial. That is the amplitude of n particle system divided by the full partition function, which is this is that capital C, right?
Yeah.
Okay, so and then we find that this expression actually is just a Poisson distribution. Okay, fine. So this is kind of this is how we would deal with, say, ideal gas within, say, grand canonical partition function. Okay, so let's now move over to quantum statistical mechanics. So again, the question is, when do we need to kind of invoke quantum statistical mechanics? And the answer is, of course, like if you're at low temperatures where the quantum effects would become more dominant and at least comparable to, say, thermal effects, then you need to kind of go beyond classical statistical mechanics. And if you have to kind of, excuse me, if you want to kind of take the quantum effects into account, then we of course have to abandon the old Boltzmann statistics kind of structure. Okay, so if one wants to do a quantum theory, then in the quantum theory, of course, anything that is observable is represented as a Hermitian operator, and the average values of these observables are written in terms of some kind of expectation values with respect to some kind of probability distribution for a state in which you are computing the expectation value. Okay, so of course, to do this, you need to have reasonably good control over the state space of the system. Okay, no, not all quantum mechanical systems are exactly soluble, but even if one has a reasonable control over the state space, one can use that to compute the expectation values of the physical observables in that and multiply that by probability of finding the system in that state. Okay, so that's where the Pn is the probability of finding the, sorry, I apologize for this capital to small switches at various places, but I'll fix that next time. Okay, and in case I don't fix it, please let me know so that like I can take care of that. Okay, so the Pn is the probability of finding a system in a given quantum state, and this is of course the expectation value of the physical observable in that state. Okay, so if one wants to get the average value of the observable in quantum statistical mechanics, then what you need to do is actually do a weighted sum. Okay, so compute the expectation value of the physical observable in a particular state and in a large number of states, and then you multiply each one of them by its own weight function or the probability of finding it. Okay, of course, Pn itself depends on the choice of ensemble. Okay, so what kind of ensemble that you want to use for the system. But besides that, there's another way of studying this, and that is to study using density matrix formulation. And this is one important concept that one uses in quantum statistical mechanics. Okay, so let's see what the density matrix story is. So suppose we have a quantum system which is yeah, we should not have switched to the next line, but it doesn't matter. So which is described in terms of complete or orthonormal set of states, say phi I. Okay, so the phi i's are the states which describe the system. Okay, and alpha I are the set of states which describe the complement of the system. Okay, so within the quantum mechanical setup, we are kind of breaking the system into two pieces. One part which we call system, which is described by class of states, which we call phi I, and then there is a complement of that, which is a class of states which are called alpha. Okay, fine. So the total, the complete quantum state of the system, which quantum state of a system and its complement, is therefore written as say psi, which is a combination, arbitrary linear combination of this type, where phi i's are the states which describe the system that we are looking at, and alpha are the class of states which are complement to the system that we are looking at. Okay, fine. Now in this setup, if you, sorry.
So what is complement? Will you please explain?
Okay, so what we are doing is that we are looking at a system. We are looking at a subsystem within a larger system. The subsystem is described by a certain class of states. Okay, but the full system may have many states. Okay. So what I'm trying to say is that, like, if you're looking at only a subsystem, then you can look at class of states corresponding to that. Okay, which I classify as phi I. Okay, anything which is not in that system would be classified as complement. Okay.
Okay.
So
yeah,
this is exactly the kind of stuff that we did in classical system also, that you look at the full system as isolated, in which you have a system and a surrounding, but the entire setup would be treated as full system. Here what we are doing is, you look at some subsystem, you focus on that and but you treat the entire system quantum mechanically. Okay.
okay.
Good. So so I mean, like, to give some simple examples,
Sorry, are we solving for the? I mean, our system in a approximate sense, like without accounting for interactions.
Approximate in what sense? There is certain amount of approximation in statistical mechanics which is always there.
Okay.
Right? Because if you have to do, if you have to keep track of every microscopic degree of freedom, then statistical mechanics is not useful. Okay. But what I'm trying to say is something like this: that imagine you have a spin chain. Okay, you have a one-dimensional lattice on which you have lots of spins. Okay, and then you write down a state corresponding to this spin chain by saying that by defining the state of every spin on the lattice. Okay, fine. Now you want to ask a question that, like, suppose I want to look at only the spin at site x is equal to x naught, and say maybe x is equal to x naught plus delta x naught, which is a neighboring site. So you want to look at this as a system, and you want to ask how this system is correlated with each other, and how this system is correlated with the remaining spin system. Okay, then the class of states which will describe only the spin at x naught and x naught plus delta x naught would correspond to the class of states corresponding to phi I. Okay, all other descriptions which describe spins at all other points, okay, would belong to the complement set. Okay, so the total system is of course complete system, as far as it's a toy model, but still a complete toy model. All possible states that you can write down, but of which there exists a subset of states which would describe the system that you have decided to focus on. Okay, it's like that. Okay. Fine. So, so once you define a state like this, which is written in terms of the state which describes the system and the state which describes the complement, okay, then you can ask that how do I compute the average value of an observable, which of course would be a Hermitian operator. Let's call it O. Then the average value of that is basically expectation value of O inside the state like this. Okay, and this quantity would be written as sum over all the states which describe the system that you are looking at, and computing the expectation value of O within the states which describe the system times a density matrix. Okay, and it is a density matrix which carries the information about how the system is coupled with the complement of the system. Okay, that information is of course there in these linear combination factors, and rho ij is written in terms of these linear combinations ci alpha star cj alpha. Okay. Now notice that rho ij is actually a matrix element of some operator that you would call a density matrix operator or density operator, and rho ij is basically the expectation value of that operator in the states of the system. Okay, fine. So if that is the case, then we could kind of use this expression, substitute this rho ij to be in that setup, and you can see that this whole thing can be written as just a trace of the observable times the density matrix. Okay, so I should have put rho hat here actually, and so expectation value of the physical observable is basically taking a trace of the operator with the density operator. Okay, and since the density operator itself is a Hermitian, it would have real eigenvalues, and we can of course choose a basis in which the density operator could be just diagonal. Okay, fine. So if one does that, then you can write down rho hat in terms of some linear combination parameter omega I times the state II, where the state I is some kind of eigenbasis corresponding to the system that we are looking at. The system, remember, is parameterized by indices ij kind of thing, and surrounding is parameterized by the Greek indices. Okay, fine. So these omega i's are basically just the overlap functions, overlap values of the eigenbasis which describes the system with the quantum state psi that describes the entire system. Okay, so in some sense kind of tells what is the kind of overlap of the state that you're looking at to describe the rho hat with the full system. Okay, now of course given the fact that this rho is describing the density or is a density operator, this whole thing should basically sum to 1. Okay, so that is this constraint, which is kind of a natural constraint on this, that if you sum over all possible overlaps, then you should be able to find your system in entirety in a bigger system defined by psi. Okay, so it's like the example that I gave. Suppose you are looking at the spin system, and then all possible configuration that, say, 2 neighboring spins at some location, say x0 and x0 plus delta x0. If you want to get a complete description of that, then you write down the eigenbasis for describing that setup, and then find the overlap of that basis with respect to the full wave function that you would write down for the entire chain. The sum over all those overlap function has to be 1, which just tells you that you should be able to find your system inside the bigger system. Okay, is that okay? Fine. So if you work in the diagonal basis, then things are a little simpler, because then you can see that your rho hat can just be written in this particular form, and you just plug it up there, and this expression or whatever, or the expression here just simplifies, and you can just write down omega expectation value, or the average value of omega, as a diagonal matrix element with respect to the eigenbasis that one had chosen. Okay. Now, of course, that is weighted by this overlap integral values, but as I said, that quantity should have sum to 1. Okay. Now, this omega I have an important physical interpretation, and that is something which is which plays a central role in, say, quantum information, for example, that is the following: that if omega I, remember, omega I would take all kinds of values, but if all omega i's are 0 except 1, okay, then the system would be, then we would say that the system is in pure state. That means this entire sum that we have written down, if this entire sum is non-zero only for a particular I, okay, then this average is just expectation value of omega in one particular state. Okay, so if only one omega I is non-zero, then one can check that this expression, instead of it being a sum, it is just one term, say II. Okay, and this expression tells you that if all omegas are 0, then the non-zero omega has to be just 1. Okay, so therefore rho hat would be just II for a fixed I, and if that is the case, then you can easily check that rho hat square would be rho hat, simply because if you take the inner product II with II, you will get rho hat back. Okay, but this expression rho hat, sorry.
So isn't omega I this mod square, what you have written?
Mod square?
Yeah, it
Omega
should be
is
ISI mod
mod
square.
of
It
square,
can be a complex
because
number, right?
rho cap is psi, right?
Oh, this one.
So when you take an inner product between I and I.
Yeah. Sorry, this should have been mod square. That's what you're saying, right?
Yes.
This expression, no? Yeah. Sorry.
Yes.
Yeah. I'll correct it. Yeah, it doesn't make sense to write just this, because this could be, may not even be real actually. In fact, it won't be real generically. Yeah. Okay, I'll correct that. Also, I mean, like, amplitudes wouldn't sum to 1. Really, probabilities sum to 1. Just okay, but coming back to this, so your omega therefore would be just 1 if you are looking at a pure state, and in that case, it is kind of easy to see that rho hat square is rho hat itself. Okay, but this is a kind of a statement for rho hat being idempotent. It's like a projection operator in that case, and that is kind of easy to see, because only if only one of the omegas is non-zero, then this is actually a projection operator. Okay, fine. But instead of this, suppose you have multiple omegas are non-zero. Okay, I mean, it doesn't matter how many, as long as it's more than 1. It could be 2, it could be 20, it doesn't matter. Okay, in that case, the system would be described to be in what is called a mixed state. Okay, and if that is the case, then you can clearly see that if you have multiple omega i's are non-zero, then rho hat square does not necessarily kind of go back to rho hat again. In fact, you can check that rho hat square is smaller than rho hat in that case. Okay, and you kind of land up with the expression, which is that for the mixed state, you find rho hat square is less than rho hat. Okay, so So I think I'll stop at this point because I kind of ran out of my notes also. But the main point here is that if one uses the density matrix description of the system, then one could concentrate on the eigenbasis of the system and try to describe the entire quantum system in terms of that basis. Okay, so that is one advantage of using this technique. Okay, so I think I'll stop here. We'll continue with quantum statistical mechanics in the next lecture, but for some time, and then switch over to critical phenomena. Okay, any questions? So I think this time around there are more typos. Like for example, this equation I'll have to take mod square here, and there's some other typos also I forgot. So there's capital P small p kind of thing, right? Yeah. Okay. Any questions?
Sir, up till now, there is nothing such as throwing away the information about the complementary states, right?
I mean, I didn't understand the question. What is the...
So we are solving this problem, but I mean,
yeah, the
as in
complement
case
is
of
not
the
playing much of a role right now, if that's what you're saying.
yeah.
Yes, true. Okay. But we may be asked, I mean, we will not do that, but like, you know, one can ask questions about how the system interacts with the surrounding or with the complement. Okay. And in that case, you would have cross correlations that, and in that case, of course, you cannot ignore alpha states. Okay. Right now, what we are doing was just focusing on physical observables like O, which describes the state of the system that we are looking at, and not so much about the surrounding. Okay, but we should eminently be able to ask and answer those questions as well. Any other question? Okay, so I just want to repeat my request again that do look at the notes, and if there are mistakes, like in the way Kaustuv pointed out just now and so on, and Harshit also, that if there are mistakes, please let me know. I'll correct those, and at least it would give a little bit of coherence to the notes. Okay.
One thing, I mean, it's not something, but here we are sort of assuming that O operator only acts on the subsystem sort of a thing.
Yes.
It does not act upon alpha.
Yes, exactly. That's what I was just saying, that we are looking at the system, we are looking at the set of operators which only act on the system, and we are trying to infer about the system. But there is no reason why one should do that.
Although later on, when we are writing that trace of O rho, that is generic.
Yeah, absolutely. This statement is generic actually, and it doesn't assume that O has to be only for acting on the system.
Yeah.
But the expression that I have written down, for example, this expression, this completely focuses on O being a physical observable of the system, and does not talk about the complement of the system. But there are various other things where you have cross correlation things, entanglements and stuff like that, for which you would have to look at operators which talk.
No, right now it does not distinguish between system and complement of the system, because I is a basis element of the total system.
That is right.
Because I is the the spectral decomposition of the whole row.
Yeah, that is right. But when one is trying to focus on the system, then you would be only focusing on the states describing the system. Okay. So if you want to ask what is the expectation value of a physical observable in the system, you don't look at what is the contribution of that coming from the surrounding. or from the complement. Okay, so for example, if the system is in pure state, okay, then only one particular state is going to contribute. All, hello, am I audible?
Yeah.
Oh, okay.
Hello.
No, it suddenly
Yes.
said my internet connection is unstable, so that's why I was a little worried. Yeah. So the thing is that, like, yeah, please. Yes.
So here, are we assuming that all i's and j's states of the system is coupled to only one state of the other part, alpha?
No. You are summing over alpha also, no? You are summing over alpha also.
Hello.
Hello. You are summing over alpha also. Look at this state.
Okay.
Yeah. So, but what I'm trying to say is that, yes. Yeah, what I'm trying to say is that, like, if the system is in pure state, then system would actually belong to one particular eigenstate. And in that case, this expression really boils down to
Sir,
describing.
actually, I think your voice cut.
Oh, I see. Oh, okay. I don't know what to do. Yeah. Just a sec. Is it any better? Hello?
Yeah, I can hear you now.
Okay.
Yeah, it's
so marginally better, is it?
yeah.
Okay. So what I was saying was that, like, if the system is in a particular state, pure state, okay, then it will be described by a single eigenstate of the system. And in that case, the expression of average value of physical observable would be really computing the expectation value in that particular state. And in that case, you are not really taking any complement into account for computing this. Okay. So in that sense, I was saying that, like, if the operator is a physical observable for the system, then you are really computing its expectation value within a particular state of the system. Hello.
Yeah, that is fine. But in like, hello.
Yes.
Can you hear me?
Yes.
Hello.
Yes.
Yeah. So what I was saying, at least in the notation, density system and the complement both, like the coupled system.
Exactly. That I agree completely.
And right now we are writing in terms of this. If our smaller system, excluding the complement, was in a pure state, then we can sort of just evaluate the
Expectation
operator
value.
on that.
Yeah.
Expectation value.
Yeah, but otherwise
But
the description is complete, includes both the system and its complement. Yes, that I agree.
Yeah. Okay.
Any other question? Okay. So if there is no question, can we kind of stop the session?
Yeah, sir. What is the book you are following?
I had given a list of names. Okay. What I'll do is that, like, I'll correct this file, and in the top I'll give the list of names. Okay. Last time I had given the names, but only verbally. I'll type them now. Okay.
Okay.
I suppose you have access to the Dropbox folder. Hello. Hello.
Yeah.
You have access to the file in the Dropbox folder, right?
I don't have Wavelength.
Okay. I'll send you the information then. Okay.
Okay.
Okay. Fine. Sure.
Yeah. Thanks.
Okay. Okay then. Thank you.